I guess a very similar question
Yeah.
for entropy, for entropy one number 4. When I was saying, like, we were given the part A, you just found like you were just going to drive an equation for where the key with just an equation with like variables rather than numbers, and
Mhm.
but then in part B, so when it said like prove that was internally reversible, I just kind of said that if the signal is 0, then that would be internally reversible. Is that kind of
Yeah,
okay?
that's right. Yeah, this is the one. Well, like in this section, there are a couple of problems where it asks you to sort of show stuff, prove stuff. I'm not really looking for like airtight mathematical proofs. I just want you to sort of understand in your own head if you spotted this, like something, this would be impossible, or this is possible, or this is reversible, or whatever. Just make sense out of, just connect the different things that you know in order to make sense to yourself about that. No one wants to see any problems specifically? Okay. All right, so last time we did an example problem where a hot steel mass was put into cold water. First, we used the first law to find the equilibrium temperature that they came to. So what's the temperature when they both are the same temperature? And then second, what we did that we haven't been able to do is we showed that it had to go from the different temperatures to equilibrium versus the opposite approach, the opposite direction. So it has to go from different temperatures to an equilibrium temperature to satisfy the second law. Well, we did this assuming that the mass and the water are both incompressible. So for this, we assumed incompressible. So now let's do something similar with ideal gases. There's a lot of stuff we know about ideal gases. Okay, so I think it's a good idea every time you see a problem that's incompressible materials or ideal gases, refresh your memory on what you know about those things, So what do we know about ideal gases? First, we know PV is equal to RT. Second, we know that the specific internal energy is just a function of temperature. Then we know that CV is equal to du dt. Cp is equal to dd temperature of H, which is dd temperature of U plus, if the definition of specific entropy is U plus PV. PV is equal to RT, so we can write this as, so that's a new expression for enthalpy. Are you with me on that? Just substituting in the other half of the ideal gas law. And so what this says, when you take that derivative, is that Cp is equal to Cv plus R. With me on that? And now there are two more things that we just learned in the second law. The first one is, I guess I'll break this up into two parts. The change in specific entropy is equal to Cp times the natural log of T2 over T1 minus R times the natural log of P2 over P1. You can also do this as an expression in terms of temperatures and volumes. So the change in specific entropy is equal to Cv times the natural log of T2 over T1 plus R times the natural log of V2 over V1. So these are approximations you can use if you don't have too big a temperature change. So this is a good approximation if you don't have too big a temperature change. And then you can also do this as the change in specific entropy is equal to this S0 at T2 minus S0 at T1 minus R times the natural log of P2 over P1. This is a more accurate way, and it's also the only way to go if you have big temperature changes. And these two things you can look up in the ideal gas table. Okay, so that's pretty much everything we know about ideal gases, about the approximations for ideal gases. So now we're going to do this example problem where we have air at two different temperatures, 2 kilograms. Okay, so we have a box like this with a little container inside. And the container inside is like that. And, with a control, we can open it to let these two gases, these two amounts of air come into contact with each other. And so we start with 2 kilograms of air in a volume of 1.6 cubic meters. At 20 degrees Celsius. And then 1 kilogram of air in a volume of 0.4 cubic meters at 100 degrees Celsius. We are going to assume that's a small temperature range. Because the final temperature is going to be somewhere in between those two. And first, we're going to calculate the equilibrium temperature. And then second, we're going to calculate the direction of this process in time. Well, one thing that's important about this is that this has to be well insulated. Why does it have to be insulated in order to do this problem for the second law part?
Because Q has to equal 0.
Yeah, right, because it has to be an isolated system, or else we would also have to calculate the change in entropy for the surroundings. And we don't have any information about the surroundings. Okay, so no material can cross the boundary and no energy can cross the boundary. Otherwise, we need to figure out what's happening outside of that too. Okay, well, if we're assuming that this is a small temperature change, we can represent the change in the air specific energy for the, well, let's call it the 20 kilogram is equal to so based on this third thing that we know here, if we look up this CV value and assume that it's constant, we can write this as the change in U is equal to CV times the change in temperature. Let's see, CV. We're going to assume, and you can look this up in that full set of tables for different gases, that CV for air in roughly this temperature range is about 0.72 times 10 to the third. That's in SI units. We're going to also assume when it comes up that, well, R for air, if you assume that the air is 80% nitrogen, 20% oxygen, we've seen this value quite a bit before, and we're going to call this 287. All right, so the change in specific internal energy for the stuff that starts at 20 degrees Celsius is 0.72 times 10 to the third.
So this is on joules, not kilojoules.
Yeah, I put this all in SI units, right?
Isn't it 287.16?
It depends. I don't know. Maybe
According to the
it's
book,
around there.
According to the book, just 287.
Yeah.
0.287.
Point two, but that's in joules.
Yeah, exactly.
I remember it.
Mm-hmm. But if you use 280's, 7.16 or whatever, like you'll get basically the same stuff, you know. And then we're multiplying this by the change in temperatures. So the final temperature, I'm going to call T equilibrium minus the initial temperature. Since these are differences in temperature, you can use Celsius. You don't have to convert. So this is T equilibrium minus 20. And then the change in specific internal energy for the 100-degree air is 0.72 times 10 to the third times T equilibrium minus 100. Since this is isolated, the first law says the change in extensive internal energy is the mass of each of these times the change in specific internal energy. So you have 2 times 0.72 times 10 to the third times T minus 20 plus 1 times 0.72 times 10 to the third times the quantity T minus 100 is equal to 0, because since it's isolated, you can't have any total change in energy. So we can divide both sides by this, and you get that 2T minus 40 plus T minus 100 is equal to 0. So you got 3T is equal to 140, and T is equal to about 47 degrees Celsius. So any questions about that? That is exactly the way we did it for the incompressible materials. By the way, you could also, so we integrated this third equation to come up with that expression for the change in specific energy. You could also, like I said, we only integrate this to use that expression for the change in internal energy when we have a small enough temperature range that we can assume CV is basically constant. Well, it also, if you had an expression for CV as a function of temperature, which you can find, and actually somewhere in our tables, it'll give you coefficients for polynomials that'll let you calculate that. Then even for bigger temperature ranges, you can get very accurate answers. The thing is, I'm using the fact that if you treat this like it's constant, you can pull that CV out of the integral, and it's easy to do. But also, if you know this is a polynomial as a function of t, you can just integrate the whole thing and you get accurate answers.
I think table A2 has the
Yeah, okay.
temperatures and we'll change in CV
Yep.
and CV.
So that's a way you could go to. The way I do it is just if I can treat that as constant, I'll do that integration. If I feel like I can't treat it as constant, I'll use these values from the ideal gas table instead. not those, but we have another set for the ideal gas table. Okay, so we got this, and now so it starts at 20 degrees Celsius in the small compartment. 100 in the small compartment, 20 in the big compartment. They meet at 47 degrees Celsius. So that's the equilibrium. So now we're going to go to the second law. And for an isolated system, we know that the change in extensive entropy has to be greater than or equal to 0. Okay, so we are going to use this equation that says the change in specific entropy is equal to Cp times the natural log of T2 over T1 minus R times the natural log of P2 over P1. That says that one thing that we need is the initial pressures of those two amounts of air and the final pressures of those two amounts of air. Okay. Okay, so how are we going to get the pressures?
E equals RT over V.
Yeah, exactly. So we're going to use the ideal gas law. So we got
Specific volumes you have to convert it to.
That's right. Yep. So we got PV is equal to RT. And so for the, I guess I started with 100 before, with the 20 before, so let's do that. So for the 20 Celsius air, we have that the starting pressure times the starting specific volume is equal to 287 times the starting temperature. 20 degrees Celsius is 293 Kelvin. The volume of the 20 Celsius air is 1.6, and that's equal to the mass times the specific volume, and so the specific volume is equal to 0.8. And so 0.8 P is equal to 287 times 293. And that tells us that this is the starting pressure. Is equal to
105,
105. Yeah, thank you. 1.05 bar. the 100. We have pressure times specific volume is equal to 287 times 373. The starting volume is 0.4, and that's equal to 1 times specific volume. So the specific volume is 0.4. And so 0.4 V is equal to 287 times 373. And what do you get for the specific volume there, or for the pressure there? 0.68?
2.68.
2.68. Yes. 2.68 bar. Okay, well, we need the final pressure too. So how are we going to find the final pressure? Once you let them mix, they have that whole volume just to mix together. And so we can treat all of it like a single ideal gas with a mass of 3 kilograms. So at equilibrium, we have PV is equal to 287 times the temperature. That final temperature we've already calculated is 47 degrees Celsius. So that is 320 Kelvin. The total space is 2 meters cubed. And that's equal to 3 times V. So the specific volume is equal to 0.6 repeating. And so 0.6 repeating times the pressure is equal to 287 times 320. Bless you. And so the final pressure is 1.38 bar. And so now we can use the second law expression for the change in specific entropy. The change in specific entropy for the 20 is equal to CV, and we're using 0.72. Okay, so this is equal to 0.72 times 10 to the third times the natural log of 320 over the 20 degrees Celsius. Starting temperature was 293. And then we're subtracting 287 times the natural log of the final pressure divided by the starting pressure and so if you calculate that, let's see, do I have that?
And if you're doing the pressure, it should be CP, not CE, or not CB.
Oh, let's see here. C. Yes, thank you. Okay, so yeah. So we know that CP is equal to CV plus R. And so CP here is CP, 1.05, 1.005 times 10 to the third. Can someone calculate this for me?
And 1.15.
10.15? Okay. And that's joules per kilogram Kelvin. And then the change in specific entropy for the air that starts at 100 degrees Celsius, 1.005 times 10 to the third times the natural log of this is 320 divided by 373 minus 287 times the natural log of 1.38 divided by 2.68. And can you calculate that for me too?
Okay,
36.5. I got 36.4. Or 40.
Okay. 36.
6.47.
Okay. Joules per kilogram Kelvin. Okay. So those are the changes in specific entropy. So now we can calculate the change in the extensive entropy. As at the 20 degrees, we started with 2 kilograms. So we have 2 kilograms times 10.15 plus 1 kilogram times 36.47. And we get a value of 56.77, something like that. And that's joules per Kelvin. The total entropy increased for an isolated system. So this is possible. So what happens if you take the other direction? Yeah, everything would just be negative. So your change in specific entropy for the 20 would be, let me just write this down once, 1.005 times 10 to the third times the natural log of, in this case, you would have an ending temperature for the 20 degree air of 293. and a starting temperature of 320. And that would give you negative 10.15.
And then you just mix that up.
Yeah. And so for the 100, you get negative 36.47. So the change in total entropy, you would end up with negative 56.8. So that's not possible. One thing, so in this case, the entropy of both of those two quantities of air increased. But that doesn't have to be the case, remember. You can have one part of your system decrease in entropy. It's just that the other part of your system is going to increase in entropy enough to make up for that. Okay? So don't make any snap judgments based on the first thing you see, in a problem like this. If something comes out to be negative for its total change in entropy, you have to see if the other parts of the system make up for that. Okay, like the example I always think of is a refrigerator. The cold part of a refrigerator, its entropy is decreasing. That's not impossible because the entropy of the surroundings is increasing more than the vegetables are decreasing entropy. And that's what makes it possible. Okay? Any questions about that approach, that kind of problem? Okay. So we've seen two of those. We've seen it with ideal gases. We've seen it with incompressible materials, how you'd go about figuring out where equilibrium is and then figuring out which direction it went. Okay, we have two more sort of subtopics in the second law. The first one is isentropic processes. We've seen a lot of properties, how to deal with processes where different properties stay constant. This is a new one. Entropy stays constant over a process. And then the last thing we'll talk about is control volumes, the control volume approach to the second law. And just like with the first law, we're going to use the control volume approach when we have devices that material is flowing through. So it's hard to keep track of an actual group of molecules, And so instead we keep track of the volume, and then we also sort of modify things based on what's flowing in and what's flowing out. Okay, so first, isentropic processes. So this is where entropy stays constant over the process. And the requirements for that. So if you want to know whether something is isentropic, this is what determines it. First, there's no heat transfer. To or from the surroundings. And second, whatever happens inside the system, there are no reversibilities. So it's internally, no irreversibilities. So it's internally reversible. So that means no irreversibilities inside the system. Okay, well, there are a lot of processes like for the compression of a piston or something, where these would be reasonable assumptions to make, you know. So using this isentropic simplification, we can deal with a lot of the kinds of processes we want to do calculations for. So if you have these requirements met, and that means that entropy stays constant, then oh, and I didn't say this, but this is only applicable to ideal gases. And we'll see why that is. Okay, so then, if it's isentropic, you have two expressions. 0 is equal to Cp times the natural log of T2 over T1 minus R times the natural log of P2 over P1. And you can use the other expression too. 0 is equal to Cv times the natural log of T2 over T1 plus R times the natural log of V2 over V1. So you can use either of those two. Well, these we can use directly if you have a reasonably small temperature range. Otherwise, let's say this one is equation A and this one is equation B. So if you have a larger change in temperature, or if you want more accuracy, then equation A says Cp times the natural log of T2 over T1 is equal to R times the natural log of P2 over P1. Remember that we have already expressed this as S0 of T2 minus S0 at T1. And so now you can say that the natural log of P2 over P1 is equal to S0 at T2 divided by R minus S0 at T1 divided by R now we can, for both sides, say E to that side of the equation. You know, raise both of these as powers of E. So we have E to the power of the natural log of P2 over P1 is equal to E to the power of S0 over R at T2 minus S0 over R at T1 and this says that P2 over P1 is equal to E to the power of S0 at T2 over R divided by E Okay, so it's all just continuing to rearrange this stuff with the exponent rules. Divided by E to the power of S0 at T1 over R. And why would you do this? That looks like a mess, but these are also in the table. And they're given the name P sub R. So P sub R, this is, the numerator is P sub R at temperature 2. The denominator is P sub R at temperature 1. And so by looking up these two values in the ideal gas table at those given temperatures, you can figure out the ratio and pressures. Okay.
What is P sub R?
I don't know what that R stands for. I mean, and it isn't anything except a mathematical thing that comes from this derivation.
Okay.
But it's just a way to get accurate ratios of pressures for an ideal gas. Okay, so basically they've done these calculations using, so remember that for these S0s, we just needed more accurate polynomial expressions for CV and CP. So they've done that and then used that to calculate these exponents, and then that's what's in the table.
Use an output and just assign something to it.
Right.
And
Right.
they have that when delta S is equal to 0, that's just saying it's so if you know you're isentropic,
Yeah.
then you can use those.
Right. That's right. So if you know you have an isentropic process and you know the beginning and ending temperatures, you can come up with a ratio of the pressures. You can also come up with a ratio of the volumes. I'm not going to go through the derivation, but as you can imagine, it's the same, similar.
So that's the V sub R.
Yeah, exactly. That's what they call it, I think, V sub R. Yeah. So similar derivation says the specific volume 2 over the specific volume 1 is equal to VR at temperature 2 divided by VR at temperature 1. And these, again, are things you can look up in the ideal gas tables. Okay, so, I think we don't have school on Wednesday. Is that, okay, we don't have school on Wednesday. So anyways, when we come back a week from today, I'll go through an example of how to use these. But remember that with ideal gases, where the process is isentropic, you can relate your difference in temperatures to difference in pressures or difference in volumes. Okay, that's all. What?
Yeah.
Oh, yeah. Yeah, it's MEA. So